for Birla Institute of Technology and Science. It's a premier institute in India, started in collaboration with MIT. He's also director of two research institutes, Vedanta Institute and IST, standing for Institute for Semantic Information Science and Technology. The websites are also same. The websites are here. And he has a master's in electronics engineering and a PhD in foundations of quantum physics. He's developing his own version of macroscopic quantum mechanics and is trying to introduce a new state of matter that he calls objective semantic information. He has published over 20 papers on this particular topic. His publications are available in the desk at the back. And one of his papers was required reading in a course on quantum mechanics at Cornell University. So he also lectured all over the world in all campuses. And with this short introduction, we are very pleased to introduce you, and we'll start welcoming him over to the class.
Thanks. Good morning, everyone. And thanks for the Paradigm Shift Club. I would like to begin the talk by first establishing that physicists do accept that they do not understand quantum mechanics. I have a series of quotations over 100 years the theory has been in existence, all from Nobel laureates in quantum mechanics, saying that theory is not yet understood. And that's Planck, Edison, is not a Nobel laureate, up there. Max Born of Born's rule interpretation. That's a 65 quote by Feynman that's well known. And here is a charming quote from Pauli about quantum mechanics. And this is Schrödinger, the inventor of the Schrödinger equation, who in 1950 wrote this, 25 years after he invented the non-relativistic quantum mechanics. He said that actually we have to go back and really think how we should have redone classical mechanics if we want to really understand quantum mechanics. I think that's an important thought. And here is Max Jammer in 75 saying that it's still an issue of unprecedented dissension. That's physical meaning of quantum theory. Delmon, inventor of quark, Nobel laureate. Quantum theory, that strange thing we all know how to use but understand very little. In other words, the fact that you can use a TV and watch shows doesn't mean you're an electronics engineer who knows how it works. You can drive a car without having to be an automobile engineer. Similarly, physicists are able to use quantum mechanics without knowing how it works. Now you can ask, how did physicists end up developing a theory that doesn't know, that they apparently don't know how it works? That's part of history of quantum mechanics, because Planck originally introduced the so-called quantum postulate in order to simply fit the available data for black-body radiation with a curve. It was just an exercise in curve fitting. And similarly, Einstein used the postulate to account for photoelectric effect, but it was more for accounting for data than starting from first principles. So he carefully titled his paper A Heuristic Explanation Towards Photoelectric Effect. For a long time, well up until 1920s, Einstein himself did not believe in the reality of photons. And similarly, Bohr he applied the quantum postulate in 1913 to develop an account of the observed spectrum of the hydrogen atom. That was just data. And when he actually simply concocted what the energy level value should be using the quantum postulate for the data to be what it was. And when Bohr did it, in fact, in the very next issue of the journal, people called it a piece of numerology and strongly objected to it. But nevertheless, there was some physical reasoning. It was not like, it was just an exercise in curve fitting. But the point is that basically classical intuitions were taken over and you applied the quantum postulate, you took classical variables, you quantized them, but it was always, right from the beginning, difficult to find the physical meaning of quantum theory. I'm not going to go into that, but we'll just take the word for all those people. Here is Braginsky, a well-known experimentalist, in 1992 saying that it's still, full physical understanding is not yet in hand. And when Wheeler was asked in 2000 for the Centennial Conference on H-bar, what should be the title of the conference, he said, "Why the quantum?" Let's have that title, because after 100 years we still do not know. This is David Gross, a Nobel laureate from Stanford in 2005. Physicists are still in a period of utter confusion. That's only quantum. CM means classical mechanics, QM means quantum mechanics. Before I get into the rest of the talk, I would like to know how many of you already feel that you have some familiarity with quantum mechanics, the two-slit experiments and all this, Schrödinger's cat paradox, measurement problem. Yeah. How many of you feel you have come in with nothing? No conceptions, no introduction. One. Okay, put your hand up. Two. Yes. Three. No. You also. Fine. Okay. Next question is, how many of you are actually physicists who have done work in quantum mechanics? Okay. All right. I have enough number of slides to explain the basic problems of quantum mechanics. I'm not going to go into them. There are useless ways of looking at the problem. Wave particle duality, cat paradox, and all this. So you'll see that later on we can give easily a one-sentence account of these problems from the viewpoint that I'm trying to develop. So I'll speak about quantum mechanics from the viewpoint, and if you didn't know any quantum mechanics previously, it's a plus. And if you knew, then you'll have to overcome your prejudices to look at this new way of looking. Okay. Quantum mechanics is a fundamentally new theory compared to classical mechanics. Well, that's what we're told. But the problem is, a lot of things about quantum mechanics look suspiciously classical. For example, there are observables called X and P. They are different from classical notional variables for properties. And these observables have operators associated with them. And these operators have a basis and, the Hilbert space, and the vectors can be, states. All that is not necessary. Just say that there are still classical kinematical intuitions at the base of quantum theory. What classical physics was totally unable to explain in around 1890, the particular features of the blackbody radiation, what's called the energy frequency spectrum. Well, you don't have to know much about it, but if you raise a black body, what it is, we don't have to worry about it. Your temperature T1, T0, and then you observe the spectrum. This is how it is. That's a maximum. And using classical mechanics, either you could just predict this, it will fail at this high frequency, and you could predict this, and it will fail at low frequency, but you couldn't predict both. So it was clearly known that classical, radiation theory will not work, and then Planck came up with a formula, and its physical meaning, Planck himself tried to understand, publish several derivations. And Planck's own motivation for developing a solution to blackbody radiation was something different from understanding blackbody radiation itself. Because the blackbody radiation was known to be independent of the material of which the object was made. You can just take an object, heat it, and cool it like a pot of milk. Just to give an example. And the curved spectrum only depended on the temperature to which you raised it. So blackbody radiation, blackbody is of course made of some material. It could be lead, it could be brass, it could be silver. According to classical physics, we would think that such a physical attribute as property as how the energies are distributed over this frequency would very much be dependent on the material of which it's made, but the formula had no reference to any other property of the temperature. So Max Planck already had a running debate with Boltzmann over the significance of the second law of thermodynamics, which says that, which asserts that entropy is always on the increase in a closed system, but actually it's only statistically valid. And it means, to put it in a very small, simple way, that if you heat a pot of milk over your stove, the milk will always increase in temperature and it'll take heat from the stove. But not always, mostly. So according to the statistical interpretation, it's possible, although with an extremely low probability, so low that it's, even given the entire universe span time, it's just not going to occur. It is possible that the cold milk will get colder and this flame will get hotter on the heat source. It's possible. So Planck did not like that idea. So he wanted some kind of an absolute interpretation for the second law of thermodynamics. And he thought that there is something absolute here, because this is not dependent on the matter of which it's made, and statistical mechanics being actually an account at the molecular level definitely depends on the nature of matter, and therefore if I could solve it, maybe I could get an interpretation of the second law that is not actually. So that was, before historically, it's an enormous number of, a lot of people have done work on Planck's own motivation to develop black body radiation, people like Martin Klein, Barry Gold, and a number of people. Kuhn wrote a whole book on this. But in any case, Planck developed that formula and he was trying to later find a derivation. And the actual derivation that starts in textbooks is something that Einstein derived in 1917. But in any case, let's come back to this theory. So classical mechanics is, when it's complete, then it's deterministic. The state is deterministic. So sometimes in classical, I should say classical physics, not classical mechanics. If the description is complete state description, you get a deterministic physics as in Newton's mechanics. And if you got probabilistic description as in statistical mechanics, which is also classical mechanics, then it means that we have incomplete state description. But quantum mechanics is a little different. You begin with something called a quantum state, and that state is one of the postulates of quantum theory that it's a complete state. And yet the predictions are probabilistic. This is a very funny thing about quantum mechanics. How is it that classically, if you are complete, then you have got deterministic, and if you are probabilistic, then your state is incomplete? The quantum theory says my state is complete, but I will still give probability predictions. That's very funny. And one more thing I should add, at the core of quantum mechanics is Schrödinger equation, which is deterministic, exactly like Newton's physics. But it has its own features, we'll see it later. Are you following just the overall idea so far? Madam?
I am, yes.
You're following it?
Yes.
Good. So, it's very simple. So far, all I have said, that's all you have to stay at this level. Much ado has been made about quantum mechanics. Most of the textbook presentations of quantum mechanics actually miss the point and misorient the student. I'll just give one example of how uncertainty principles start, and why I think it's different. It should not be taught that way. In any case, we'll get to that. So right now, we're simply thinking classical mechanics, then quantum mechanics came, and we know quantum mechanics came because classical mechanics failed, and we know that now that quantum mechanics is completely a non-classical radical theory, that means we should try to understand quantum mechanics without using any of classical ideas. Well, we do. And so that's not so good. And so we want to see how we can avoid that. So in classical mechanics, actually there is nothing called a classical state. So you have an equation of motion, which is probably in school we have all learned, F equal to mx2 dot, and if you, I mean, inside this, there is, of course, if you integrate this twice, you'll get one constant of integration v naught, and then you'll get another constant of integration x naught, and this, along with mass, is supposed to specify the state of the classical system. So if you know x and p naught, which is mv naught, then at any time, then you know the state of the system. And if you specify the state of the system, you know both. That's the idea. But in quantum mechanics, as I said already, the state specification, so in classical mechanics it's unique, but in quantum mechanics, due to uncertainty principle, which is not how I would put it, but I'm just putting it so it's easier for you to understand. But actually, I would say it's due to operator non-commutativity. I'll talk about it a little bit later. So in quantum mechanics, due to uncertainty principle, the state specification can only approximately specify x and p, because x and p obey an equation called delta x delta p is greater than or equal to h bar. So they cannot be simultaneously arbitrarily known to any accuracy, and therefore, the state. So in some sense, in this state, the quantum mechanical state has less classical information. I should put it like this. Yet we deem quantum theory to be a more fundamental theory than classical theory. Why is that? This is worth asking. Why would this quantum mechanical state from a classical viewpoint have less information than classical mechanics? And yet it's a more fundamental theory. Maybe that the actual information that quantum mechanics contains is not about position and velocity. Maybe the theory is more fundamental, and maybe it has some other information that we are failing to actually note at the time of observation. It's possible. It's like, computers basically to give a silly example. You start a computer and every time it makes all kinds of buzzing sounds, and you think that this device is made for making that sound. Well, maybe that's true, but actually it's meant for running an operating system and do calculations. That's a deeper understanding. So in fact, or there's a TV and you think it's a chair. Well, it'll work as a chair pretty good, but you can never figure out why inside the TV there's so much circuitry, see? And then suppose somebody starts explaining why these circuits are there inside to make it a chair, because other chairs don't have that. That would be weird. So something like that might be happening in quantum mechanics, that you have actually what's called the Hilbert space. And if you just look at it from a statistical viewpoint, an ensemble viewpoint, you get classical information, right? It's like using this entire quantum mechanics as classical theory, but then you have to ask the question, why does this have this complex, beautiful, mathematics, which we didn't need in classical mechanics? Like other chairs didn't have all those circuitry that's inside the TV. Why do we need to use this expensive thing as a chair? And then if suppose you try to give an account of what's happening in Hilbert space in terms of what's happening in space and time, it'll be just bizarre. And that's what most of popular writings on quantum mechanics are. It's just a bizarre, they should simply say, and that position Einstein took, for example, they should simply say this theory is only about actually a behavior of an ensemble of particles, means many number of particles, and we don't know how this theory describes the individual particle, or maybe we need another theory. Einstein didn't even hedge his bet. He said, we actually need another theory for a single particle. I think he was not correct. So my own idea is, there is some animal called psi function, pronounced as psi. Excuse me. And my own idea is that, expectation is that this psi function actually has got two ways of being linked to observations. You see? And one way is the current, what you call the standard quantum mechanics. The other way is what I call as NQM or macroscopic quantum mechanics. That's what I'm developing. But the general idea is that quantum mechanics is statistically complete in this way of looking, but it's ontologically incomplete. And in this way, you will actually get the picture of the single, quantum object. I don't say electron or photon. I say single individual quantum object, IQO. And it will also give new predictions. There are two ways of looking at the theory. That's my approach. So I'll give an example for this. Suppose you have a text passage, English text passage. This idea is often used in artificial intelligence. Suppose you take a textbook, a book in English, and let's assume that you're someone who doesn't know English. For you, these are all just shapes, different shapes. There are 26 shapes, you may notice, and they occur in different combinations. And now you could count what is called the relative frequency of occurrence of letters. And it is known that in any natural language passage, if it's written according to the rules of grammar, then different letters have some stable frequency patterns. It is known I will occur for 7% of the time in any passage like that. Certain words will occur in certain combination of letters, etc. So it is possible to entirely view the passage simply in terms of a statistical analysis of the letters of the language treated as shapes. And any new passage that's written in English will follow this. It will not violate the statistics. But you will never know why a single sequence of letter shapes appeared the way they did in a particular place in the book. For example, you saw a sequence of these shapes like this, band. Why did it occur? From entirely within the shape view of the passages, you can't tell, but if you had the semantic view of the book, if you understood the language, you might say, oh, this is a book about Bay Area rock music history, and therefore the word band came. Or you might say, this is a book about atomic spectra, and therefore the word band came. That's a totally different explanation. So is it the case, and I'm going to make in a very outline form a case for that, and is it the case that the observations that we see currently in quantum mechanics, which are always in the form of, there's only one kind of observation that physicists can ever make. Only one kind of observation physicists can ever make. It is the observation of a meter needle on a calibrated scale. That's all. Now there could be equivalent ways of doing this. You could think in terms of an auditory click, or a bright spot in the photographic plate, but they all actually reveal a position measurement. So position measurement is the only measurement you can make. Every other measurement is actually inferred by doing an analysis of the experiment. The current basis of physics, the concept of position as the most basic kinematical idea, maybe that's wrong. Maybe while we are looking at this, there is another information measurement that you can make, even with this very measurement when the meter needle is pointing to +1. I just presented a paper on that at a conference in Sweden. It's coming in a volume of proceedings to be published by American Institute of Physics. And that, I'm just giving you a thought. I'm not going to explain all this. If it is there, then maybe these are two ways of looking at the observation, exactly like there are two ways of looking at the letter shapes. Either it's a shape like that, or you say it's an A. And there are two different ways of them totally actually relating to the world. And maybe because we are staying within this and trying to understand individual occurrence, that we have all the problems. It's possible. It's logically possible. In other words, the quantum theory is a theory only of some classical physical way of looking at the world of observation. Not electrons and photons, but I'll explain it a little bit more. And maybe there's a quantum way of looking at this world of observations. And if we do that, maybe we'll get a deeper understanding. And that makes sense because quantum mechanics is not just a theory of photons and atoms and electrons. It's also a theory of rocks and chairs and everything. So, but we don't know how to apply it to the big world because we have assumed the big world to be in some sense classical, and we have tried to apply to the little world, and in the little world we only get probabilities and we are not getting actually causal explanations. Knowing this is much more important than knowing the cat paradox and wave particle duality and stuff like that, because those are all problems perceived in this way of looking at quantum mechanics. Those are problems that arise when you use quantum mechanics to describe the single system in this approach, where it's only good for ensemble of. And these two things are very important to understand about physics. I'm sure that most of you will think that physics tells you how things happen in the world, isn't it? If you know, but actually it's wrong. You know, that view can no longer be maintained. Philosophers know it. It is known as the failure of scientific realism. You know, the idea that physics gives an understanding of the world that exists independent of us and how it works. It's a huge topic. You know, I'll give the conclusion of those types of studies. What happens is there is something called a real world. We must accept that if you want to do physics. To that extent, I accept, and I'm a realist. So when I say physics does not describe this world, I'm not saying that physics, that there is no reality, physical reality. It is. And physics actually plays a particular role. I'm going to try to explain it. So there's a real world. The nature of this real world you cannot know. None of us can know. We don't even know whether something like that exists, and it is not required in order to live successfully in day-to-day life. But it can be logically questioned. It's practically useful, pragmatically useful, but it's logically questionable. It's very important. In other words, if the mother tells, the child, okay, I'm leaving lunch for you when you come back from school in the cooler, and you take it and she goes to work, and let's say she believes that I have put a real box of lunch in the refrigerator which is real, and that when my child comes, she will see it. But actually, it is not necessary to have that viewpoint to live successfully in the world. Okay, I'll just explain that a little. In fact, we can even go to the extreme of saying that it is only an approximate way of living in this world, and quantum theory actually hints that there is a better way of looking at this world. That's going to be my statement. Now, there is a guy called René Descartes. He's a French mathematician, pure mathematician, top class. And he's the guy whose work we all study in school, known as coordinate geometry or algebra and all that stuff. You're talking about x-axis, y-axis, and coordinates. A point has got two coordinates, x, y. All that Descartes did. Did you study that at school? Yeah, everybody knows. Are you able to understand it better now?
Cartesian coordinates.
Exactly. They are called Cartesian coordinates. Exactly. Descartes had another preoccupation too, besides mathematics. And he came before Newton, which means he came before modern science as we know developed. And he had another preoccupation. How can I show that science is possible? And Descartes was actually thinking, how is science possible? Now, why should he think like that? Because you must remember that he came at a time when knowledge was supposed to be obtainable only through the scriptures. Christian scriptures, no doubt, in the European world. And it was the same elsewhere too, in places like India. And Descartes thought that this is not a dependable way of getting knowledge. And of course, you see, already Aristotle had thought that you can get knowledge only by studying God in the world. There was this idea of going outward that was already there in Western thought. And he then wanted to show that we should get dependable knowledge by studying the world, but he was so clever that he realized that a theologian can easily trip me up. If I told a theologian, sir, you are just an armchair philosopher, you are sitting and reading some book, and then telling us, what the world is like, what's space, what's time. But I want to study things in the world. I know for a fact that this exists. I'm very confident of that. I'm going to study. He realized a clever theologian could tell him, excuse me, sir, what's your name? Descartes. Oh, I see. So let me tell you that your belief that there is a chair is as much your imagination as anything else, and you are doing no better than armchair philosophizing. If you think that you can study the world, if you realize that. And that is a problem that's not solved until today, as far as. What is that? So why did Descartes realize that this chair is not as real as it seems? Because, to put it in a modern language, I'm going to just very quickly tell you, Descartes argued like this, effectively. Descartes argued that, look, I'm not looking at the chair, I'm looking at the light that's reflected from the chair. And then he said, I'm not even looking at the light because the light is falling on my eye, and the eye is I'm casting his argument in modern terms. And the eye is, having a retinal image, that's what I'm looking at. So when I say, I'm looking at a chair there, I'm looking here. And he said, I'm not even looking here because this image is sending me some signals, afferent signals into my brain. He assumed he had one. And then, all I'm seeing is actually how my neurons are firing. So I may say there is a chair there, but I'm looking here. Then he said, I'm not even looking here. Because I'm just having an experience. I'm not experiencing neurons firing and then interpreting it as the chair. But I'm just feeling there's a blue chair. So he said that all I have are first-person accounts of my experience using ordinary language. It's going to turn out to be very important. You try to understand this. This is an irrefutable argument, and today it's known as the Cartesian skepticism. Cartesian, you can Google it and you'll find it. Descartes said that I can doubt near everything in existence. How do I not know that some clever person, God, maybe created, he called a demon, but it could be God, that he created an illusion for me such that everything appears to be real, but maybe nothing like that exists. It's a very huge point. And I might give one more lecture here, then I'll go into that deeper in quantum mechanics. This is known as Cartesian skepticism. So Descartes showed that all you start with are your experiences, personal experience. And everything is my experience. The fact that I see somebody here sitting and writing something, that's my experience. I don't know whether he exists. And even if I went and touched him and I said, oh, that's real, but that's just a touch experience. It's as far removed from reality as my visual experience is. If I smell something, everything it's all my perception. So he said that the fact that something exists the way I perceive it, it's called visibility. What I see is what I get. Something that exists exactly the way. Or if you want to be a little philosophical, all philosophers try to state everything simple in more complicated terms. So the philosopher should say that the assumption that the form of my experience has a one-to-one correspondence with the structure of the world. See, that's a big way of saying, but a simpler way of saying is that the belief that whatever I see is what is out there. He said, it's a belief. Especially in modern times, we can very easily understand that. Suppose you look out of the window, so I look out of the window, or door, whatever it is, I see trees and stuff, some people walking, fine. I say that's what it is. But then, unbeknownst to me right now, someone put a huge TV screen with a 3D projection, and I just went and opened it and I saw the exact same thing, but I don't know that that's just a projection. You see? And somebody tells me the second time you saw, that was not real, there was a projection. I said, oh, really? And then he says, okay, now you go and look. Okay. And then he says, is it real or projected? I cannot tell. In other words, the idea is that your experience is not sufficient to actually infer reality. Wow. That's very nice. This is a very strong, and quantum mechanics is going to come to that if I get to that in time. So to please try to understand this, there is first of all, I should really put reality here. I should put reality here. Reality is a bigger word. So we should first of all believe, if we want to do science, that there is a reality. And then we have to believe that the best way to think of that reality as a world. Okay? And then we have to think that this real world is perceived by each one of us, and that philosophers has called as phenomenal world. Phenomenal world is a world that's produced inside you because you interact with the world. The phenomenal world is a world that's private to us. See, this blue chair is my phenomenal object. You see a blue object as your phenomenal world. So now, why do we actually all think that there's an external world? Now, you see, that I'm coming to show now why realism is not necessary to even to live in the world. Suppose you say that experience is only experience when it is described using language. So let's say that if I look at this, I just have a cognitive state. In philosopher's language, it's semantically neutral. But if I describe it, then it becomes an experience. I can say there's a blue chair. Now I could say looking at it is my mother's gift. So you see, my experience is not determined by my perception, but my description of that perception. And this is my own point in philosophy of science. But if you do that, then we all have a description of our own private phenomenal worlds, and it has some common points. It is not the case. You may say that you're looking at the back side of the chair, I may say I'm looking at the front side. So your phenomenal experience is different from mine. But we may generally agree that it's in this location of the world and it's got certain color. So the intersubjectively invariant portion of our private experiences, as expressed in ordinary language, is actually the reason we believe there is a reality behind our perceptions. But we could all live in Krypton or some planet where we all agree that there is no reality and we just have language, and that wherever our language coincides, we have communication, and where it doesn't, there is no communication. We could say that. And you could live in the world equally well. In this sense, the belief that there is a chair in the world is not necessary. But of course, we want to do science, and so we want to say, no, there is a reality, and we want to understand. But you can't go so far as saying that we are going to directly experience. That claim of physics is not sustainable. Why? I'm going to the next point. See, this is a problem that has not been solved for 100 years. Please try to understand this. You saw, I showed you 100 years of quantum physics that we don't understand. And in 100 years, if you make a rough calculation of 10,000 universities, each producing 10 to 15 PhDs, you see, in maths, physics, and chemistry, all of them would have thought of the quantum mechanics. It's actually approximately about 25 million scientists over 100 years. Nobody has even a clue what's the problem. So I'm just giving you directly the way to approach it, but if I discuss the problem also, I can do it. That'll be interesting too, but I won't. Okay? So what happens is you have the real world, then you have the phenomenal world, and then you have something called the mathematics world, which I will for short call it as the physics world. The physics world is also created private for a physicist. But this language is ordinary language, or OL, ordinary language. And this is called theoretical language, or TL, and it's mathematical. Mathematics is totally abstract. You see, it has got nothing to do with experience. For example, if I write like this, 1, 2, 3, what have I written? What have I written? 1, 2, 3, what are these? Numbers. These are not numbers. These are symbols for numbers. Because in Sanskrit you can write 1, 2, 3 in a different way. In fact, even in our notation I can write 1, 2, 3 like this. There's nothing to stop me from writing 1, 2, 3. So all simple. So what are numbers? You can Google this. That's a question that's unsolved in mathematics for 2000 years. No one knows what is a number. Big mathematicians have taken different views on it. There are different schools of thought. You see? There's Platonic realism that Gödel subscribed to. There is actually conventionalism that Poincaré subscribed to. There is formalism that's Hilbert subscribed to. There is intuitionism that Brewer and others subscribe to. There's all kinds of jungle there. Don't get there. You will be lost. So what numbers? It's an abstract thing. So out of that, so the mathematics world is abstract. It is expressed using another language called mathematical language that has no connection to the real world, exactly like the phenomenal world doesn't have. But you see, the phenomenal world we believe has a connection because it's practically useful. Like I said, if you leave your lunch in the refrigerator, it stays there when you come back in the night. And you can microwave it and use it. It looks fine. There's nothing that questions it. It appeared, and I'm going to show you quantum mechanics questions that. In other words, quantum mechanics has nothing to do with electrons and protons being different from classical world. But quantum mechanics has everything to do with the macroscopic world actually being different from classical. In other words, the classical conception of the macro world is not the only conception that we can have. That's what we're going to go towards. So basically this world is connected to the real world only through connection to phenomenal world because it makes predictions. I should give you a separate lecture on what physics is, but I have a paper called Physics and Common Sense. You can read it, and all these points are very elaborately discussed there. So now, because it makes predictions in the phenomenal world, and the phenomenal world is connected to the real world, we used to think that this world is real. See, it's very indirect. Did you get this point? This world is entirely abstract, but it has no connection with either this world or this world, as it is, it's mathematical world. But when the mathematics is used in physics, something called state preparation, observation, and all that stuff, then you can connect it to the phenomenal world through predictions. What is a prediction has to be explained. You get solutions to mathematical equations, and you get real numbers, and these real numbers will show up as meter readings. I'm not going to go into all of that. So just take it for granted. These are very precise ways of stating everything. A physicist might say, oh, I don't have to believe in all of that. I can believe that particles exist in this world. And yeah, but that's like, ordinary person saying, I don't have to question the reality. Sure. Now, that would all be fine and dandy if quantum mechanics hadn't come. And we're going to show that quantum mechanics just, challenges everything in the world. So predictions, it connects to the phenomenal world. And because the phenomenal world we believe is connected to the real world, we can say physics is connected to the real world. Okay. So what happens is really in science, and I'm coming to conclusion here. So now, there are two things, sir. In the laboratory, you do an experiment. Okay, and what is an experiment? You do something and you observe something. Do, see, that's all. For example, I do something. I put it at the edge of this table. And then I just put it, move it a little bit. It fell down. So right at the instant when it started falling, I have prepared the state of the system. And I have actually a stopwatch with me, and as soon as it starts falling, let's say I'm accurate enough to click it, and then when it makes a sound, I stop it again, and then the thing I started reading is pointing to +7. That's all this experiment. Do, see. It's not just an experiment, it's just doing and seeing. It's not like, just going here and then see. This is not an experiment. No, it's done under very controlled conditions, very defined conditions, and you get a number. This is described using ordinary language. That's what Bohr is saying. The word experiment can in a sense be used only in referring to a situation where we can tell others, ourselves and others, what we have done and what we have learned. That's all is experiment. Then you remember you got in your times piece, I know the height of the thing, and it was reading to plus 2 in this case, 2 seconds into it. Now what happens is there is a mathematics world, physics world, in which there is something called a particle that moves, and it moves according to some equation, s equal to ut plus half at squared, and you plug in these values, u is 0, because you just, that's why I was so careful. I didn't impart any velocity to it, and I just dropped it and it fell down. And then I give the value t here equal to 2, u equal to 0, and height I know, maybe whatever it is, 17 inches. If you solve this equation, I'll get the same reading I got. So this world is actually entirely mathematical, and this world is entirely ordinary language. These are two parallel things going on. The only way they meet is by a very complicated process of, solving the equations and getting real numbers and designing a clever experiment in which those numbers will appear as meter readings. That's what, and that's what the physicist gets paid for, which is not much, by the way. The thing is that, in other words, he's appreciated for making this connection between what he was visualizing and what you can see. Believe me, if you do physics, that's something fantastic. And the feelings you get when you do that, you cannot understand unless you are a physicist. It's a moment of great revelation. There's no doubt about that. It's of the same quality as religious experience. And that's what the physicist lives for. Okay? So what happens is, this idea that mathematics cannot reach out to the real world is the same in classical mechanics as in quantum mechanics. There's just no difference. It's not different at all. You will see the stuff, and the next slide is very important, but I'll just put this. This is what most every physicist thinks. That because atomic behavior is so unlike ordinary experience, it is very difficult to get used to, and it appears peculiar and mysterious to everyone. You see? So in other words, he's saying atomic behavior, which is described by what? Ordinary language or mathematics? Can somebody say? It's described by the mathematics, and he's not careful enough to make that distinction. That behavior connects to predictions through physics, which is exactly like any other ordinary experience. He doesn't see that. So he says it's so unlike ordinary experience. What does that mean? And it is difficult to get used to, and it appears what he's trying to say is that if I visualize the mathematics of quantum theory using ordinary language, like waves and particles, there is some contradiction which is unlike, the way ordinary language works in ordinary level. Actually, know that the mathematics has nothing to do with the experiment, and if at all we use ordinary language to describe it, even in classical physics you say electromagnetic wave, that's not a real wave. All waves have got a medium, but electromagnetic waves don't require a medium. It's an approximation, it's an idealization. The truth is in the mathematics, the ordinary language is just a way to do things. And you can do it equally well in the atomic world if you accept something called complementarity. I'll come to that. So, both the novice and the experienced physicists, even the experts do not understand it the way they would like to. And here he's talking about understanding the mathematics. And it's perfectly reasonable that they should not, because all of direct human experience and of human intuition applies to large objects. He says, we know how large objects act. All of this must be self-evident. The idea that physics describes the real world is not sustainable. The physics world is entirely abstract and mathematical. This is true of both classical mechanics and quantum mechanics. In classical mechanics, the abstract mathematical formalism can be named and described using ordinary language terms. For example, if you say F equal to ma, you can, write F is a force. It's a very abstract idea. Force is not the same thing that I use to move this. It's not force. In physics, it's very different. And the quantum mechanics too, this is possible if you accept complementarity. Complementarity simply means at different times I speak in different tongues and you should be complementary. That's the simplest definition of complementarity. In some experiments I will say it's a particle, and in some other experiments I will say wave. In the same experiment, at one stage I will say it's a particle, at another stage I will say it's a wave, and you shouldn't come over. Why? Because I'm a quantum physicist. But why does that give you a right? Well, because it works. And then why don't you then make sense? Because I don't know how it works. All this is called complementarity. But it has got a nice name. That's what it is. Actually, I wrote a paper showing what exactly is Bohr's interpretation, and that's so in quantum mechanics too we can do that. So ordinary language in physics, this is my conclusion. Ordinary language in physics plays two roles. One to describe the experiment, and one to give an image of the physics world in terms of particles, motion. It's an image that you construct. It's an abstract image. This is first. It has to first of all be able to describe the experiment, and then we can get a picture. My claim is that in classical mechanics, oil is adequate for both jobs. It is able to describe what we do in the world. Like I said, that I'm pushing this pen, nobody is going to question it. If the pen fell down, nobody is going to question it. Or if I just threw it like that, everybody knows that it went up and came down. Classical mechanics is good enough to describe what I do in the laboratory and to also visualize the mathematics. But in quantum mechanics, it is not even good enough to describe your experience. Why? Because if you said, assuming quantum mechanics applies to the macroscopic world, if you said that this actually went a definite trajectory in order to reach that point, if you say that any object, small or big, in going from A to B, followed a definite course, quantum mechanics says it's wrong. But you say, I can see this. You may see it, but that's what you see. In other words, this Descartes' argument now kicks in with tremendous force. It says you are seeing, having an experience of the pen falling, but in reality something else is happening. And quantum mechanics says when you make a measurement, whatever else is happening appears the way you see it. And no one knows what is a measurement. So unlike Descartes, who suspected that the experience could be otherwise, reality could be otherwise than what experience suggests. Descartes could not say what is reality. Quantum mechanics goes further than Descartes. It says not only experience can be other than how you experience, it says it is, and it is a psi function. I'll have to get into quantum mechanics in more detail next time. So this is what quantum mechanics says. Quantum mechanics says that there is a reality, and this reality is called the wave function, and when you actually experience it through your senses or through measuring devices, then you get an experience that is totally different from this, not even anywhere close. It mathematically proves it. And it says that if you want to actually know what that is, and quantum mechanics doesn't say, I say it, we should actually go from here to here. We should get a new language to talk about this world. And this language of thinking that there are people and tables and chairs, it's not going to work. And this is mind-boggling. It's much more mind-boggling than cat paradox. Are you following what I'm saying? So now I can give you a one-sentence description of cat paradox to show you how thorough this is. What is cat paradox? Cat paradox simply says a cat cannot be simultaneously dead and alive. We know that. So all the quantum mechanics say, cat paradox says is A, quantum theory applies to the big world, cats and chairs, as good as to the small world. Right now we have started by applying to the small world, and if you extend this to the big world, it won't work. That's all it says. Because if you extend it to this world, cats have to be dead and alive. So it's much more reasonable to say, you can't take the existing quantum theory and apply it to the macroscopic. That's what Schrodinger said. We have to go back 300 years and redo classical mechanics. You don't have, but he didn't see that you don't have to redo. His own physics is actually for quantum macro world, But I'm saying you have to change the way you look at the ordinary world in order to understand quantum mechanics. And that is something that physicists cannot even think of. Not only that, I should have put that quote here. I'll just take this 1 second to show you that's the most important quote. It is so profound that I must put it. Nobody take this seriously, but Bohr knew this. That's why Bohr is Bohr. Niels Bohr, who wrote so much about quantum mechanics, and everyone who tries to understand quantum mechanics has to think about what Bohr did and said, and who nobody understands. You know, a sentiment on Bohr said, we can't understand Bohr. This Bohr only at one point. Which point? The very first article we wrote in M-Man in 1920, in one place, namely the first paragraph, he made the statement, never again ever he made it. Because he didn't want to bring anybody's attention to it, in my opinion. He said all new experience, meaning observations, must make their appearance within customary points. He said, we can't change the way we look at the world. He said. That's not true. We do that all the time. People fall in love and marry, and after 5 years, he asks them. They have a totally different opinion of the other person. Excuse me. You know, I'm joking. But not only that, I actually found a way how to look at this world differently. That I don't have to think the long way. But that's what makes sense. So according to me, to cut to the chase, as I say, I just pick up this American expression, not to use them. The idea is that quantum physicists do not get to understand quantum mechanics because they have figured out a way to use that theory using customary ways of looking at the world. But if you want to understand it, you have to change to a new way of looking at the world, which is not simple.
If we look at rotation supercooled fluid, it is in our world, in our classical observation, it ain't classical. What we see in the classical world isn't explainable in the classical world.
Okay. I will differ there.
You would differ with that?
Yeah.
Yeah.
Because I would differ because you see when you have everything, let's look at the world Bose-Einstein quantum state, what we call quantum phase transition. You see, the observations are still statistical predictions about user behavior. There's no other way we can actually get at the psi function directly. And I think we need to, and we can. To me, and the way I understand it, the progress from Bohr's 1925 to, say, by the time Josephson junctions came around and squids came around and all that is, we have known now how to go beyond psi squared use of quantum theory, which is just probability predictions, to psi. Because psi itself, in the supercooled temperatures, has a deep value wavelength which has got macroscopic dimensions. But the predictions are still the same kind. I haven't really worked out this thought too well. But that's kind of how I think.
In your opinion, what do you think is stopping us from being able to describe quantum mechanics in ordinary language and microscopic?
Wow. I mean, I can give you a physics answer
Works to
and the simple answer, common sense thinking I could give. But I'll try to. What stops us from thinking in this new form, assuming that quantum mechanics demands that we actually shift our perspective? Or why can't we just do it easily? What stops us? Maybe if mathematics is involved, it might be difficult. But you're saying it's just ordinary language, right? Why can't we do it? Good question. I want to give a reasonable answer without having to give another big lecture. Hold on. Answer is this. One word.
Say it a little more.
Reification, to reify, is the tendency to take our experience and project it outside of us. That's called reification. It's a projection. In other words, there is really no outside world. What we have is a world in our experience, phenomenal world. And I reify and create an external world. From that now I want to understand my experience. That's very difficult. Why would I read a book, a recent New York Times list, seller list, thriller, and I'm just looking at paper and ink, and I'm saying, wow, it was so thrilling reading this book, it was fantastic. How could this paper and ink, which if I had given you separately as 1 kilogram of unprocessed paper and 1 bucket of ink, would have never produced that. It's producing all these thrilling experiences in you. It is known as the problem of qualia in cognitive science, perception problem. Why is it that if the world is just nothing but atoms in motion and void, as the Greek thinker thought, why do we have this rich world, this tapestry of experience, that white wall and the ground, white roof and the ground wall, it was beautiful lady, and maybe this flatter her a little bit, Why is that? Why does he have a beautiful green jacket? We don't know. You follow what I'm saying? This is wrong. And why did it come? Einstein very succinctly described it. He said the job of physics is to describe the world as it exists independent of our experience. Now, I'm saying, if you think of actually the world in terms of your experience, see, two extremes will not do. This is known as naive realism, that there's a world existing out there. It doesn't work. Then there's something called idealism. It's all in the mind. That's obviously nonsense. The table is not in my mind because this blue chair is not in my mind, then why don't I see it here? There's something in the world that constrains my experience. So idealism is wrong, naive realism is wrong, then how to get out of it and do science? So we should change the physics perspective from saying instead of thinking of the world as it exists independent of my experience, let's think of the world which gives rise to my experience. Are you following? That world you can easily think of. Because we cannot think like that. So another next answer is that everybody has got experience. I don't know who was that. Kipling, who said east is east, west is west, never the twain shall meet. Right? Because at the time British colonization was there, they all went to India and they said, this is a bizarre way of thinking Indians. It has nothing to do with us. Why? Because in the West, we take an experience and we want to understand the experience, the nature of the experience, the world, the object. But in the East, they will take the experience and they wanted to understand the nature of the experience. So two diametrically two different ways of thinking. I am actually bringing in a synthesis of the two by saying, let us think of the experience as a conjunction of the experience and the experience, and still we can study the world objectively. I mean, I have to say a lot more. Did I respond?
With the experience quantum mechanics?
Yes.
Actually, what you're asking is that let us think of the experience as a what?
Conjunction. As a conjunction. Conjunction of two. I mean, that's a rough way of saying I'm not satisfied. I have to say much better, but it takes longer time. It involves both. Yes.
Would it be accurate to think that perhaps the object of experience of experimentation is ought to be the experiencer?
No. See, I would say, in fact, instead of the word conjunction, as you said, I would like to use the word relational. Do you follow? Suppose if I take this as a classical object, this is the answer, sir, to your question. This is the real answer to your question now. If I take this object, classically, it's a mass point. That's what they say. But I know it's gray and there's black things and all that. But take one aspect of it. suppose I say that it's a paperweight. It's a paperweight. Now this is not a property of this object by itself. It is only in relation to a stack of papers. Are you following? Imagine a world in which there was no papers, then this cannot be even potentially a paperweight. So if there are papers in the world, this is potentially a paperweight, but when you actually put it on top of the stack of papers, it becomes a real paperweight. That's exactly what quantum mechanics says. The quantum object has got potential properties, which are described by complex amplitudes. And when you actually make a measurement, which means you put it in relation with the macroscopic experimental arrangement, you get some actual, the same property actualized. So it is this relational viewpoint that I'm trying to, and that requires a new language at the level of physics. Does that make sense?
Yes.
In other words, we also know that you are nobody by yourself unless in relation to other people. So then potentially you could be something. You see? So it's very similar to that, but at the level of objects. This is what has been misunderstood. As quantum mechanics is saying it's really something about the experience. No. It's closer, getting closer, but it's still out there. What Sartre called as bourgeois, non-psi. My being as myself and my being in relation to others. And in relation to others is all false. My beingness with myself is just what it is and it's nothingness. These are all philosophers doing their work. But this is science. This is not philosophy.
So what you're offering is basically a new relational viewpoint.
Yes. Not only that, in that viewpoint, the psi function becomes the state, quantum state of the source, and not the emitted electrons. I mean, you got to pay a lot if you want to understand. You can't get a cheap way out, like in the theory or collapse and decoherence. Nature has thrown a real curveball to us, and you got to hit a home run. That's a very American example, isn't it? Not bad. Shall we stop? I'm available for further discussions, but at least follow me.
Any more questions?